A warm welcome once again to ET Auto and to this very special webinar on the topic of need and solutions for controlling evaporative emissions in Indian scenario. This is, ladies and gentlemen, the first edition of a webinar series co-organized by ET Auto and ECMA, that's Exhaust Controls Manufacturers Association. And we will, in each of the webinars in this series, will delve upon a very important and pertinent topic each. And we will have an industry expert who will take us through the theme of the webinar and also delve into the various aspects of the subject in question. So today's expert is Dr. Terry Latham, and it's my pleasure to introduce him. Dr. Terry Latham is the Manager of Technology and Regulatory Affairs at Ingevity Corporation and currently serves as the International Chair for the Manufacturers of Emissions Control Association, that's MECA, and is a member of the Emissions Control Manufacturers Association of India. He brings over 12 years of experience in the fuel and automotive emissions control industries with specialized expertise in evaporative emissions. Terry has contributed technical guidance to regulatory and industry stakeholders across the United States, Europe, Brazil, China, and India. He holds a PhD in Earth and Atmospheric Sciences from the Georgia Institute of Technology in Atlanta, where his research focused on the impact of pollutant emissions on air quality and climate. So, and a little bit about the agenda we have today on the topic. Across India, petrol-powered internal combustion engine, which is ICE vehicles, emit significant amounts of volatile organic compounds, VOCs, through evaporative and refueling processes emissions. Emissions that often far exceed those from the tailpipe. Who would have thought, right? Usually when we talk about emissions, we more often than not talk about the tailpipe emission levels. These emissions, the evaporative emissions, are also qualify as a silent threat, as they occur primarily when vehicles are not in use, such as during parking or refueling, unlike exhaust emissions, which are only produced during vehicle usage. India's hot summer months are quite popular, and when the air quality tends to be at its worst. Evaporative emissions of VOCs from petrol-fueled ICE vehicles can reach up to 30 grams per vehicle per day. That's a significant. And if you add up the whole vehicle park in India, that's a significant amount of emissions. This is more than 10 times higher than the corresponding tailpipe emissions of VOCs. Very important, therefore, to focus on this type of emissions, which are usually not talked about, as I said, not discussed about much, but nonetheless, they deserve to be really highlighted well, and also find out ways to how to contain these emissions, and also protect the environment by doing so, not to mention the savings that we will have in terms of fuel usage. So, well, that's what the context is. Over the next hour and a half, we will really delve deep into this topic, thanks to Dr. Terry Latham and to your participation, the audience. Please make the most of it. Please post your questions in the Q&A box, and we will have Dr. Latham answer them. And of course, I'll also have my own share of questions to him, but that will be after a very comprehensive presentation by Dr. Terry Latham. The stage is yours, Terry. Over to you.
All right. Well, good afternoon, everyone. Thanks for the the kind introduction, was discuss the purpose of today's webinar, which is titled Need and Solutions for Controlling Evaporative Emissions in the Indian Scenario, is to really discuss the relevance and growing need to control evaporative emissions in India, discuss the issues and impacts of evaporative emissions specific to the Indian climate as well as Indian conditions, and to give an overview of global regulations in this area. And then finally, we'll talk about some of the present status and cutting-edge technological solutions to help reduce evaporative emissions and how these are deployed in different regions of the world. And then finally, highlight how India can achieve substantial evaporative emission reductions through regulatory and technological measures. And so we're pleased to present this webinar through ET Auto, as well as the Emission Controls Manufacturers Association. So I want to spend a few moments just talking about the Emission Controls Manufacturers Association. It is a nonprofit association established in 2002. It consists of 19 global manufacturers of emission control equipment for automobile, off-road, and non-road engine applications in India. ECMA is closely associated with the Association for Emissions Control and Climate, often referred to as AECC, in Europe, as well as the Manufacturers of Emission Controls Association, MECA, in the US. Ingevity, the company I work for, is proud to be an associate member of ECMA. We are also members of MECA. ECMA member companies have been operating worldwide and share a lot of experience and have a proven track record in research and development, manufacturing, testing, and integration of a variety of advanced emission control systems that include exhaust emission controls. These are catalytic converters, catalysts, heated tubes, oxidants, gasoline particulate filters, as well as the evaporative emission controls, which we'll be talking about today. And these are control technologies that are applied across the wide range of the vehicles. So this includes two-wheelers, three-wheelers, cars, light commercial, heavy commercial, and off-road applications. So through these webinar series, ECMA is engaged to provide expert guidance and inputs, and we provide this input to policymakers, regulators, equipment manufacturers, and other stakeholders to make them aware of emission control strategies and technologies, particularly when discussions around new emission norms are being brought forth. So for example, ECMA members are actively participating in a variety of Bharat 7 panels that are being formed by the Standing Committee of Emissions as well as the Automotive Industry Standard Committee. ECMA organizes conferences, seminars, roundtable meetings, webinars to share knowledge and share experiences in the area of on-road and off-road engine emission controls, focus on improving air quality and controlling emissions while also enhancing fuel economy. I'd like to draw everyone's attention to ECMA's 16th International Conference, ECT 2025, which will be from the 7th to 8th of October in New Delhi. So welcome everyone to register and attend that conference, where there'll be a wide range of ongoing discussions. So through these webinar series, the objectives is to share knowledge with ECMA's family of experts in the areas of relevance and interest for today as well as for tomorrow. We would like to disseminate information about cutting-edge technologies and our robust solutions that offer ECMA members as well as the OEMs to meet the current and forthcoming stringent emission regulations with the array of fuel options and technology solutions. I'd like to enhance the visibility of ECMA in the automotive world through ECMA's power and knowledge of expertise, encourage skill development, and provide opportunities for collaborative and participative activities. I'd like to update on emission regulations, policy implications, and solutions, and hope that we all learn from these interactions. So as noted, this is the first in a series of webinars, and so happy that you're all able to join us this afternoon. So before we get into the topic, also we'll just provide a brief introduction to the company that I work for, Ingevity. So just at a glance, we are an international company in the performance materials and chemicals space. We engineer and manufacture activated carbon products through our performance materials business, which is primarily used in gasoline vapor emission control systems for internal combustion engines, hybrid electric vehicles, cars, trucks, motorcycles, and boats. Our performance materials segment serves customers globally for 3 manufacturing sites, which are located in the US, and then 2, which are located in China. And then we supply automotive parts to 2 component manufacturers throughout the global automotive supply chain. Our products are also sold into food, water, beverage, and chemical purification markets. And we also have a performance chemical and advanced polymer technology segment, which we won't be talking much about today, but we do offer a variety of solutions in automotive coatings, as well as in road technologies and road construction applications. So just a quick snapshot of our global presence. As I noted, we have manufacturing operations in the US and China, but we then have also technical labs and resources within India, as well as within Europe. And this is again to support our automotive customers globally. And there's just a little bit about some of the products that we produce as Ingevity. We'd like to say that we're committed to purifying, protecting, and enhancing the world around us. So all of the products that we produce either enhance efficiencies or reduce emissions in some way. And so when we think about our automotive segment, we've estimated that up to 8 million gallons of petrol are saved globally by our activated carbon products every day throughout all the vehicles that are used around the world. When it comes to things like road construction, we have additives that can be added to asphalt paving that also reduce volatile organic compound emissions when doing paving operations. And again, these have environmental benefits. And then other segments of our business, we touch on bioplastics, we provide additives that help make components fully biodegradable in home and industrial composting, as well as marine and freshwater environments. We produce chemicals for crop protection that enables less pesticides to be used, as well as to improve the durability and longevity of those products. And then we're also in renewable energy and fuel. I know compressed natural gas is an important the fuel for the Indian market. And so we actually have technology solutions using some of our activated carbon products that can be used to store natural gas onto vehicles to enable dual fuel platforms. So these are diesel absorbed natural gas platforms that we use primarily for larger commercial applications, as well as some segments like school buses. And then finally, we're also in safety road striping, where some of our resins are used in reflective road striping, which increases driver safety. So you can see across a wide range of products, we touch a variety of products that people use every day, but we are a kind of an intermediate in that process, where we produce products that we then sell to customers to ultimately make those final products. So now that you've learned a little bit about who ECMA is, as well as Ingevity is, let's now get into the topic at hand, which are what are evaporative emissions. So during the course of the talk today, I hope that the audience will walk away with an understanding of what evaporative emissions are, how they relate to exhaust, how significant they are in India, how they're measured and regulated, and then what can be done to improve the control of these in India. And just to give an example of, as was mentioned kind of in the introduction, that evaporative emissions are oftentimes not discussed very often. They're not well understood. So as just a kind of a fun experiment, I decided to ask the artificial intelligence to draw me an image of what it thought evaporative emissions from a vehicle would look like. And the image on the right is the example that was first generated. And you can see it's quite a futuristic looking type of automobile. It did understand the concept that evaporative emissions are some type of smoke or vapor, but you can tell from this image it didn't quite fully understand exactly where they come from the vehicle. So in this case, it's thinking something like an engine, but coming from a tire. So again, quite a futuristic looking example, but not the best image for what evaporative emissions are. And through some just kind of prompting and coaching to the artificial intelligence, over time, I was able to get it to generate an image that looks a lot more reflective of the actual scenario. So you can see in this image, this is just an image of a fuel cap door open, where you can see now it's depicting some vapors escaping from that open fuel cap. And so this is a better representation of what evaporative emissions are and one of the potential sources where they can occur. So let's just talk about an introduction to vehicle emissions in general. There are a lot of different sources of emissions that come from vehicles. And when I talk about these sources, I'm not just talking about light-duty vehicles. This can apply to any category of vehicle, whether it's two-wheeler, three-wheeler, light-duty, heavy-duty. Most everyone is familiar with the term exhaust emissions. So this is coming from the tailpipe of the vehicle. You're emitted at a single point from a single process, combustion. You can see these, you can hear them. They only occur during vehicle operation. The pollutants that are often emitted from the tailpipe could include particulate matter, particle mass or particle number, nitrogen oxides, volatile organic compounds, carbon monoxide, carbon dioxide, and water vapor. And the amount and types of species varies depending on the type of fuel that's combusted, the engine conditions, etc. So there's a variety of different exhaust emissions that can be emitted. And these are controlled through the introduction of catalytic converters, selective catalytic reduction, particulate filters, whether they be diesel particulate or gasoline particulate filters, as well as OBD leak detection to prevent leaks before getting to those control technology solutions. When it comes to evaporative emissions, this is emissions that's not often well understood. This can come from multiple points. It could come from the fuel tank vent, the lines, as well as non-fuel materials, and from multiple different processes. They're invisible, they're silent, but they can occur at any time. They can occur when the vehicle's operating, they can occur when the vehicle's parked. The only way that you'll know that typically they're there is if in high enough concentrations, you might be able to smell them. So some non-fuel based, if you're ever familiar with like the new car smell, those are volatile organic compounds that are emitted from some of the components like the plastics and the leathers in the car. But then if you've ever smelled petrol around a refueling station, those are the evaporative gasoline vapors that you're smelling. Evaporative emissions contain volatile organic compounds, a wide variety of different volatile organic compounds. And the fuel-based evaporative emissions, so those that come from the evaporation of fuel, are controlled via an activated carbon canister that's located on vehicles. And this is a technology solution that exists for petrol-fueled vehicles, any category of petrol-fueled vehicle. And we'll get into the technology and the different options as we go through these slides. And then OBD leak detection is also important for the control of evaporative emissions. Another category of evaporative emissions is refueling emissions. These are emitted during an active refueling event because you're filling a tank with liquid fuel. So as the tank fills with liquid fuel, the air in that tank has to be displaced. And so it's pushed essentially out of the tank as it fills up with fuel. Those vapors contain, again, the same VOCs of evaporated fuel vapors. And this is controlled either on the vehicle with an activated carbon canister system called onboard refueling vapor recovery, or it can also be controlled at the petrol station through something called stage 2 vapor recovery. As we go through the talk, we'll talk about these technology solutions and their pros and cons in further detail. And then finally, we have non-exhaust emissions. So this is a kind of newer category of emissions that have come up over recent years, particularly with the introduction of Euro 7, where there are now emission limits and standards related to brake and tire wear emissions. Evaporative and refueling emissions are a category of non-exhaust emissions, but they're oftentimes not discussed at the same level that you often hear with brake and tire particulates. So the focus of today's talk is, of course, going to be on the evaporative and refueling emissions. So before we get into detail relating to evaporative emissions, one of the key concepts that needs to be understood is related to volatility and vapor pressure. Understanding these two concepts provides the foundation for understanding why evaporative emissions from petrol vehicles can be so high in India. The first fundamental point is petrol is a volatile liquid. It evaporates quickly into the air. So if anyone has spilled petrol, you'll know that you smell it almost immediately, and it will evaporate in a short amount of time. Compared to diesel, which has a lower vapor pressure than petrol, diesel evaporates more slowly. So if anyone has spilled diesel, you'll know that it hangs around a lot more. It's often stickier. And this is, again, just due to the fact that diesel has a much lower vapor pressure than petrol. Another important fact is that vapor pressure varies with temperature. Higher temperature means that more molecules have the required energy to evaporate. So if you look at the figure on the right, you can see just at low temperature, there's less energy. So there's less of those molecules that are going from the liquid phase into the gas phase. But as you heat up a liquid, particularly a volatile liquid, a lot more of those molecules have the energy to escape. So it's the same as when you put a pot of water on a stove to boil. Those water vapor molecules will, as temperature goes up, those water vapor molecules come off more and more. You have steam, and eventually the water fully evaporates. So temperature is a very important factor, particularly for volatile liquids such as petrol. When you place petrol inside a closed container, some of it will evaporate into the air. This is just because the liquid and the gas always seek to achieve what we call equilibrium. As temperature increases, more petrol evaporates into that space, which exerts pressure. And so when you think of a fuel tank, which is on a vehicle that's filled with petrol, as that fuel tank heats up, vapors are generated, pressure is generated, and then those vapors have to go somewhere. And so if there's not a control technology on the vehicle, or the control technology is not sufficient to capture those vapors, then you have release of these volatile organic compounds into the atmosphere. Petrol is not a single component. It's composed of a large number of hydrocarbons. Each component has a different vapor pressure and boiling point, and this just adds complexity to the types of volatile organic compounds that are emitted over time. But the fact still remains that as temperature goes up, more of these species tend to evaporate, and so you have more volatile organic compound emissions. A common measure of the volatility of a fuel is what we refer to as the Reid vapor pressure, or RVP. So if I use the acronym RVP, I'm referring to this standard measure of volatility of petrol. And this is defined at a given absolute vapor pressure at a given temperature of 37.8 degrees C. So it's a standard ASTM method for determining the Reid vapor pressure. And so if we look at the Reid vapor pressure of different fuels, you'll notice there are significant differences. So as I mentioned before, when you look at diesel, which is shown in blue, the vapor pressure of diesel is generally less than 1 kilopascal. If you look at ethanol, pure ethanol, E100, it has a vapor pressure of around 18 kilopascals. Pure petrol, which is E0, has a vapor pressure generally between 56 to 60 kilopascals. And then when you introduce ethanol into petrol, one of the effects that occurs is that it increases the vapor pressure of the base fuel. So petrol, whether it's E10 or E20, will have a slightly higher vapor pressure than pure petrol. And that oftentimes ranges somewhere between 60 to 70 kilopascals. And so this is important because as we think about the types of vehicles that need control, the types of fuels that are important for evaporative emissions, is traditionally the petrol E0 or the petrol ethanol blends that are the greatest impact and importance for controlling evaporative emissions. In India, the fuels include ethanol, which when blended into petrol increases the vapor pressure. And this increases the evaporative emissions. So from April 1st of 2025, BS6 vehicles are certified to E20 reference fuel, which is the specifications allow a maximum RVP between 60 to 65 kPa, which is within the range that we saw for E20. E20 commercial fuel in India, this is the fuel that's allowed to be dispensed to the petrol stations, allows a maximum RVP of up to 70 kPa. And this is again just to allow for the fact that when petrol or ethanol is splash blended into petrol, there is an increase in the RVP. So there is a higher RVP allowance for the commercial fuel relative to the certification fuel. This higher vapor pressure of E20 relative to E0 is one of the things that leads to higher evaporative emissions and higher vapor generation. So if we look at the figure on the right-hand side, if the vapor pressure in kilopascals is on the y-axis and the ethanol content is on the x. And you can see that for E0, the vapor pressure is around 60 kPa. As you move to E5, E10, and E20, that vapor pressure increases, from 75 back down to maybe around 65 kPa. As that vapor pressure increases, what you also see is the relative vapor generation rate, which is what's shown in red, increases. This is, again, just the potential for evaporative emissions. So again, with these ethanol blends, the relative vapor generation rate is higher. So as much as 25% higher for an E5, and then coming down to maybe 5 to 10% higher when you look at E20. And this is a significant impact as we'll see in some of the later slides. And it requires significant amounts of ethanol blended into petrol before you reduce that impact of the blending. So it takes more than E50 to E70 before you get to a vapor pressure that is back to where you were before you added the ethanol. Another important fact with ethanol is it can increase the permeation of fuel vapors through the fuel tanks and the vapor lines, increasing the evaporative emissions. And this is because the ethanol itself is a polar molecule which it tends to interact with those materials and allows for swelling of those polymer materials. And this then allows both the ethanol as well as some of the aromatics and other petrol components to essentially permeate through those materials over time. And so materials with permeation barriers, specific materials that prevent that ethanol permeation, are needed as ethanol content. So automotive evaporative emissions are a mix of non-fuel based as well as fuel-based evaporative emissions. These are any of the emissions that escape into the atmosphere that occur from any vehicle, particularly vehicles with petrol fuel tanks. So the non-fuel-based emissions include things like tires, paint, plastics, and adhesives. These are highest for a new vehicle, and then over time, they will reach a steady state. And so oftentimes, before a vehicle is put through a certification test, these components are what we call aged to allow them to reach a non-fuel background type of level. The fuel-based evaporative emissions are much higher than these non-fuel-based emissions, and this comes from sources such as the fuel tank, the fuel lines, connectors, and seals, the fill pipe and fuel cap, and the air induction system. So essentially any component on the chassis of the vehicle that is in contact with fuel has the potential to be a source of evaporative emissions, whether it be through permeation of that material, through escape of vapors, or leaks in that system. A key point with evaporative emissions is they occur even when the vehicle is not operating. So there are a variety of sources that can occur when the vehicle is off. The first of those is what we refer to as hot soak. This is essentially the 1 hour period that occurs after you turn off your engine. So when you've driven your vehicle across the city, the vehicle heats up over time just due to the engine, due to the exhaust gases, temperatures from the environment, the road surface. All of that serves to heat up the vehicle, and vapors generated as the vehicle heats up. So when you turn off the vehicle, there's a period of essentially cool down, and vapors generated as heat transfers from the engine, the exhaust, and from the road after the shutdown period. So that 1 hour period is referred to as the hot soak period. And when we get into the testing, this is a specific test that is done for the vehicles where there is a 1 hour hot soak test. The second source is what we call diurnal emissions. These are vapors that are generated in the fuel tank during the daytime temperature rise. So again, if your vehicle is just sitting outside, parked, as shown in this figure here, during the heating of the day, the temperature of the vehicle will increase, and the temperature of the fuel in the fuel tank will increase as the temperature increases. The higher the temperature outside, the more the fuel tank increases. Again, as we learned earlier, temperature is a key component to the volatility. So as the temperature increases, the evaporative emissions increase. And these are referred to as the diurnal emissions. And there's a specific test to test for 1 day diurnal, 2 day diurnals, or even 3 day diurnal. So it's how long you park your vehicle, and you essentially test that over a given temperature profile. As we discussed, there's also permeation emissions. This is when vapors diffuse to the rubber and plastic components. This occurs at any time. And then finally, there are leaks in the system. So if there are any leaks, whether they're vapor leaks or liquid leaks, these through any holes in the fuel system, this becomes essentially the point of least resistance, or it's a point before the emission control system. So it can become essentially an uncontrolled emission source if there are liquid or vapor leaks in the fuel system. So those are the emission sources when the vehicle is off. There's also emission potentials when the vehicle is driving. These are referred to as running loss emissions. And again, this is just due to the fact that as you operate a vehicle, the longer you operate that vehicle, the warmer the vehicle gets due to the heat from the engine, heat from the road surface, and that tends to increase the temperature of the fuel in the fuel tank. When you're driving, you can also be actively moving the fuel in the fuel tank around, something we call fuel tank sloshing. That agitation of the fuel can also serve to increase the evaporative emissions in the tank. And so again, this is just a source of evaporative emissions that can occur when the vehicle is operating. And then finally, there's an emission source during the petroleum refueling. The vapor in the fuel tank is displaced by adding the liquid fuel, and that vapor then has to go to some type of control device, or it escapes to the atmosphere. So now that we've talked about the different types of evaporative emissions, why is it so important that we control them? Well, evaporative emissions are volatile organic compounds, which are one of the major contributors to the formation of particulate matter and ozone in the atmosphere, which creates smog and haze. There's a lot of documented evidence looking at the impact of volatile organic compounds on the formation of these pollutants. And so the more these pollutants are emitted, the higher the concentrations are in the atmosphere, and the more these reactions can take place. And these reactions oftentimes take place during the summer seasons when you have evaporative emissions are at their highest levels. And this is when oftentimes in many different cities across the world are when you see the greatest concentration of these types of smog and haze events. And it's reducing air quality that is what's led to a lot of the regions of the world to adopt measures to reduce volatile organic compounds, including measures to reduce evaporative emissions from vehicles. In the United States, that was one of the key measures that led to the adoption of the technologies that we'll be discussing about during the call today. Evaporative fuel vapors also contain a variety of hazardous air pollutants. One example of this is benzene, which is present in the fuel, which is harmful to health and can cause cancer through long-term exposures. And then finally, without sufficient regulations and control, evaporative emissions are essentially uncontrolled, which means it's just a essential waste of petrol and money. It's like letting some of your hard-earned money just evaporate into the air. You pay for the fuel. You would like for the fuel to stay on the vehicle to be used to drive that vehicle. You don't want the fuel essentially just evaporating into the air over time. So the control technologies are not only important for improving air quality, but for keeping valuable fuel on the vehicle to be used. If we look at the market of vehicles in India, petrol engines and evaporative emissions are most prevalent for two-wheelers and passenger cars. And so if you look at the figure on the right, it's showing the proportion of the fuel type based on the vehicle category. So for passenger cars, in 2024, more than 60% of the vehicles sold contained a petrol engine, whereas the remainder involved diesel, compressed natural gas, or battery electric. For two-wheelers, it's predominantly petrol engines, but battery electric vehicles are gaining traction over time. And then for three-wheelers, it's a more diversified mix of petrol, compressed natural gas, and battery electric vehicles. So there are over 18 million two-wheelers that are sold in India on an annual basis. And these have an average fuel tank size of about 10 to 15 liters. And then there's about 4 million passenger vehicles sold, which can have an average fuel tank size of between 50 to 60 liters. So even though two-wheeler sales are 4 times higher than the passenger car sales, evaporative emissions from passenger cars can be equally important because the average fuel tank size can be 4 to 5 times larger than a two-wheeler. So again, the larger the fuel tank size, the more fuel, the more potential for evaporative emissions. Another important factor to focus on passenger vehicles is that petrol engine sales have significantly increased following a decline in the share of diesel passenger vehicles, which were about 33% in 2019 and currently stand around 18% after 2020. And this kind of sudden decrease in diesel engine sales came after the introduction of the Bharat Stage emission standards. Evaporative emissions are measured in what is called a sealed housing for evaporative termination. This is essentially a large chamber, which we refer to as a shed. And so the figure on the left is one of these sheds in a certification laboratory. And the door that you see here on the lower kind of right-hand corner, that's a door that can be fully opened to allow a full vehicle to be pushed inside this shed. And so the evaporative emissions are done on the full vehicle. It's a full vehicle test in an enclosed environment. And that is because, as we noted before, evaporative emissions come from a variety of different sources on the vehicle. So you can't just place a sensor in one location and get a representative measurement of the evaporative emissions. You have to measure the emissions coming off the entire vehicle. And that includes the non-fuel sources as well as the fuel-based sources. These sheds are used to quantify the hot soak emissions, the diurnal emissions, as well as the refueling emissions. And since it is an enclosed environment, you're also capturing the non-fuel background, the fuel permeation, as well as evaporative emissions that come from any leaks in the system. For the diurnal test specifically, the shed is cycled over a certification diurnal temperature profile. And that is a representative one is shown here on the right-hand side. So the current Euro 6D diurnal temperature profile starts at a temperature of 20 degrees Celsius, increasing over 12 hours to a maximum of 35 degrees Celsius before it cools back down to 20. So that profile of going from 20 to 35 back to 20 is what we call a one-day diurnal temperature profile. Based on different regulations, these diurnals can be 1 day, 2 days, or 3 days in length. And again, it's because you're trying to simulate the diurnal emissions that occur when a vehicle is parked. And for a lot of vehicles, those vehicles can be parked for multiple days. So 1 day or 2 days or even 3 days or more. And so regulations use this shed, and they establish the temperature profile, the number of diurnals, and an emission limit. It's the combination of those three factors which determine the stringency of the evaporative emissions regulations. And that stringency of the regulation then also drives the technology control response that is put on the vehicle to control for those emissions. And so if we look at different markets across the world, one of the things that we will see is that there is some level of regulation on evaporative emission for passenger cars and two-wheelers, but the stringency varies. So if we focus first on India, the current regulation is BS6, which is through a standard procedure called AIS 137. This particular standard does not include the onboard refueling, and it's a one-day diurnal test with a 2 gram per test limit. So going back to that shed that we looked at earlier, the vehicle is placed in the shed. It's run over 1 day of diurnal temperature profile, and the emissions that come from the hot soak, the background, the diurnal, the permeation, all those emissions cannot be higher than 2 grams per 24-hour test. There's been a recent notification to go adopt to a BS6 phase 3, which is also the introduction of the WLTP drive cycle. And as part of that notification, there will be a new test procedure referred to as AIS 175. And that procedure does not include the onboard refueling standard, but it includes a 2-day diurnal test. And so India will be moving from a 1-day test to a 2-day test with the same limit. And this is proposed to take effect around the year 2027. And with this 2-day test, one of the things to note is, again, the vehicle is put in that shed. It's run over 2 diurnal temperature profiles. And so in this case, it's the hot soak plus the day 1 plus the day 2 plus as the permeation factor has to be accounted for. And the combination of those emissions has to be less than the 2 grams. So you can see moving from BS6 to the BS6 phase 3 does increase the stringency because it is moving to a 2-day test. If we look at Europe, in Euro 7, the initial proposal that came out from the Commission was quite a robust and stringent standard. It included an onboard refueling test of 0.5 grams per liter, which is similar to the standards that are adopted in other regions of the world. And it included a much more stringent hot soak and diurnal test. In this case, a 2-day 0.5 gram test. And in the case of this particular standard, it was a 0.5 gram per day limit. So the maximum of day 1 or the day 2 emission results from the shed could not have exceeded 0.5 grams. But as many of us know, with the Euro 7 regulation, the final regulation was different from the Commission proposal. And it was significantly weakened due to Europe's focus on electrification, particularly for light-duty vehicles, where the current regulations on CO2 require all light-duty vehicles to be electric by the year 2035. And so as part of the negotiations, the political negotiations that took place during Euro 7, the final regulation eliminated a lot of the regulations that would have driven control technologies on both the exhaust and the evaporative side for combustion engine vehicles. So the final regulation in Europe for Euro 7 did not include the onboard refueling standard, and included just a modest reduction in the evaporative hot soak and diurnal limit from 2 grams to 1.5 grams, which in our experience is not going to lead to any changes over current Euro 6D canister systems. If we look at other regions of the world, you'll find that evaporative emissions are regulated to a much greater level of stringency. The most recent region to adopt more stringent regulations was Brazil. Brazil introduced within PROCONV 7 a onboard refueling standard of 0.5 grams per liter, as well as a 2-day diurnal standard of 0.5 grams. So you can see what the Commission in Europe initially proposed was very similar to the regulations that are currently in force in Brazil. China has a very similar standard currently, China 6B, where there's a refueling standard of 0.5 grams per liter and a 2-day diurnal test of 0.7 grams. China is currently in the process of developing a China 7 regulation, and we anticipate this 2-day diurnal standard to shift to a level similar to the US standard. So a further reduction in the hot soak and diurnal limit. And then finally, the US has the strictest evaporative emission regulations of any location in the world, with a refueling standard of 0.5 grams per liter. But then when it comes to the evaporative hot soak and diurnal emissions, it is a 3-day test at 0.3 grams per day. And so this is a combination of a much lower limit plus 3 days, which leads to the increased stringency of the US test procedures. And then finally, if we look at 2-wheelers and 3-wheelers, BS6 is equivalent to Euro 5. There is no onboard refueling standard for 2-wheelers or 3-wheelers. The evaporative hot soak and diurnal standard is 1.5 grams per test, but a key difference when it comes to this category is this test is measured over a 1-hour heat build. So it's not a 24-hour test, it is a 1-hour test. In 2022, the California Air Resources Board had proposed a 3-day diurnal standard of 1 gram per test. But this proposal is currently on pause because, as many of you might be aware, there's currently ongoing differences between the federal EPA as well as California in terms of California's authority to establish more stringent emission limits than what the federal EPA requires. And so until that uncertainty is resolved, a lot of the California proposals are currently on pause. So how is the fuel vapor captured before it gets to the atmosphere? There are several main components of the evaporative emission control system. The first primary component is the activated carbon canister. So as we talked about earlier, the fuel tank on the vehicle is one of the major sources of the evaporative emissions. And so as that fuel tank increases in temperature and the vapors are pushed out, they are pushed first to an activated carbon canister system. The activated carbon is specifically designed, has a specific pore structure that is designed to capture those hydrocarbon vapors and store them on the carbon. So as fuel vapors get released from the tank, they're directed to the canister and the canister stores them. A canister only has a certain amount of capacity. The canister cannot store these vapors indefinitely. So once the carbon in the canister becomes saturated with fuel vapors, that canister could then become an emission source. And so it's very important that the activated carbon canisters are sized appropriately to manage the fuel vapors that are expected to be generated during a variety of different in-use scenarios. That canister is then also connected through lines to the engine where there is a purge valve. And this purge valve, this canister purge valve, is another very important component of the evaporative emission control system. When the engine is on, the vehicle's operating, this valve can be commanded by the engine control module to open this purge valve. And what that does is it allows the engine to draw the fuel vapors out of the canister and use them for combustion. This is a process that we call purge. And this is the process by which the canisters are continuously regenerated to be used again for future diurnal or parking events or refueling events. And so it's this constant loading and purging of the canister which enables this system to continuously work for the life of the vehicle. Without sufficient purge, the carbon would become saturated with fuel vapors and become an emission source. And so again, it's just this closed loop system that enables the canisters to be a source of storage of those vapors, but then the engine purge allows those vapors to be used for combustion. So it prevents emissions from going to the atmosphere and allows them to be used to operate the vehicle. You then also have the canister vent valve, which is the valve on the canister, which allows, during the engine purge, fresh air to enter that system. And then it also then allows the canister to vent because the fuel tank systems for most vehicles cannot be pressurized to significant levels for safety reasons. And so if there is a significant amount of evaporative emissions generated, they will first go to the canister, but it cannot stay a closed system. And then finally, you have a fuel cap, which seals the fuel system from the atmosphere, but also allows for the refueling. So now we're just going to look at some examples of canister systems. So for 2-wheelers, which have small fuel tanks, you'll often find a relatively small carbon canister system because canister systems, again, are often designed to manage the fuel vapors that are generated from the fuel tank. And so smaller fuel tank systems will oftentimes have smaller canister systems. So if you move to a larger fuel tank, a 13.2 liter fuel tank on a two-wheeler, you'll see that the canister size typically increases. So in this case, it was a 0.36 liter canister. If we move to light-duty vehicles, which could have upwards of 60 liter fuel tanks, if that vehicle does not have refueling control, then the canister systems are often around 1 liter or less. If it's a 60 liter fuel tank with a refueling control standard, those canister systems can be 2 liters or larger in size. And when we get to some of the later data, you'll see the importance of this larger canister size, because it not only controls for the refueling emissions, that larger canister capacity is also very important for controlling the diurnal emissions that occur during parking. So first, we're going to talk about refueling emissions, which can be quite significant without proper control. And so what we're going to do now is look at infrared videos of different refueling events. As I mentioned earlier, evaporative emissions are really difficult to see with your eye, and they're generally non-visible. But through the use of infrared technology, those evaporative emissions, those hydrocarbons, can be visualized. And so what we'll be looking at here is first a refueling of a vehicle that has no control technology for refueling. So there's no onboard refueling vapor recovery system, and there's no stage 2 system on the petrol pump. So again, as this fuel tank gets filled, the vapors are going to escape out of the point of least resistance, which is out the fill pipe. So you can see here on the visible infrared image, the vapors that are coming out of the fuel tank around that nozzle during the refueling process. During a refueling of a 50 liter tank, 75 to 100 milliliters of liquid gasoline escapes during that process. So if we just put that into real economic terms, if petrol cost 100 rupees per liter, filling a 50 liter tank would cost about 5,000 rupees, and about 7.5 to 10 rupees worth of petrol purchased would be evaporated every time a refueling event takes place. And this occurs for each vehicle. So you can see this would add up quickly over time. We can now also look at refueling emissions if we have a stage 2 vapor recovery system. So this is a system that can be installed at the petrol station. And the way stage 2 vapor recovery typically works is the nozzle is replaced with a nozzle that can pull essentially an airflow through that nozzle. So essentially it's designed to capture the vapors actively coming out of that filler neck during the refueling event. But due to a variety of different factors, the efficiency of stage 2 in use can range between 50 to 70%. And so as we look at these images, one of the things that you'll notice is depending on the calibrations, inspection, maintenance, how well the seal is on between the nozzle and the vehicle, all can affect the vapor recovery efficiency. And this can range for the worst performing systems to essentially no control to upwards of 50% for better performing systems. Another important point to think about with these stage 2 systems is you're actively capturing the vapor from the nozzle and you're directing it back to the underground storage tank. That underground storage tank then vents through a vent pipe as shown here. And so if there's not controls on the vent stack, it's essentially taking the emissions from one point and they can then be emitted out of another point. And so there are a variety of limitations that can exist with stage 2 systems. The first of which is not every petrol station may have stage 2. It requires rigorous inspection and maintenance to maintain the certification efficiency. These systems often certify to levels of around 85% efficiency, but experience and use suggests these efficiencies can deteriorate and be as low as 50%. And finally, petrol storage tank vent stack emissions are generally not controlled as part of stage 2. And so the captured refueling emissions can just simply vent out of these vent stacks, which further reduces the efficiency. This loss of vapors is not something that is accounted for when calculating the efficiency of stage 2. So during stage 2, 23 to 50 milliliters of petrol for 50 liters of refueling can be evaporated into the air. And then finally, another solution for controlling refueling emissions is what is referred to as onboard refueling vapor recovery. This is the installation of a larger canister system on the vehicle, changing some of the refueling pipe diameters and lines to enable the vapors, rather than being directed out the fuel fill pipe, they're directed to the activated carbon canister on the vehicle. So when there's ORVR on a vehicle, there is no need for a stage 2 system to actively try to pull the vapors from this refueling operation. They are directed to the canister where they are sufficiently controlled. And the control efficiency of these onboard refueling vapor recovery systems has been demonstrated in the US to be 98% efficient. So as we watch this video here of a vehicle that is being refueled with an ORVR system, you can see clearly here there's no visible emissions, even through the infrared camera, being emitted from this refueling event. And this is, again, just demonstrating the 98% control efficiency of the ORVR system. So in this case, less than 2 milliliters of petrol per 50 liters would be evaporated. An important point about onboard refueling vapor recovery systems is that they're fully implemented in the US, Canada, China, and Brazil. And specifically within the US, we now have over 20 years of in-use experience and compliance data on these ORVR systems. So all vehicles in the US have to undergo in-use verification testing at both low and high mileage conditions. And so we have over 20 years of that data, and that data has continued to show that ORVR systems maintain this control efficiency of 98% for the full life of the vehicle, with no maintenance required on those canister systems. And so refueling emissions can be significant without the proper control. So in some cases in India, there is no control of refueling emissions. And in those cases, if you're refueling at a station that has no control and your vehicle has no onboard control, anywhere between 7.5 to 10 rupees worth of fuel is evaporating during that refueling event. If the station has stage 2, the stage 2 efficiency could vary significantly, just depending upon the inspection and maintenance and operation of that particular facility. Again, demonstration, US had stage 2 in the early 90s, and the US EPA, as well as the California Air Resources Board, determined that the maximum efficiency that could be achieved from those systems was 70%. So over time, the US has decommissioned the stage 2 systems in favor of the onboard refueling vapor recovery systems. And so if you're refueling at a station that has stage 2, depending on the efficiency of that system, the loss of value in fuel could range between 2 to 5 rupees. And then finally, if there's an onboard refueling vapor recovery system on the vehicle, 98% of those refueling vapors could be maintained on the vehicle. And so it would be a very small loss of value in that example. So the type of technology is very important for controlling refueling emissions. And to put this into comparison to exhaust emissions, because one of the things that's often not thought about is, well, how do these refueling and evaporative emissions compare with exhaust? So the current exhaust standard for a Euro 6D vehicle or a BS6 vehicle is 68 milligrams per kilometer. That is the maximum amount of hydrocarbons that are allowed from the tailpipe during a certification test. So it's 68 milligrams per kilometer. Based on a car's fuel tank size, as well as its fuel economy, we could determine how many miles a car could drive on a full tank of petrol. And so what I've done here is just essentially estimated what the emissions would be, exhaust emissions would be, for driving a full tank to empty. And that comes out to about 50 grams of emissions from 768 kilometers of driving. If we compare that to the refueling with no control, you can see that the refueling emissions that occur over that few minute refueling event are comparable to the emissions that occur over the full range of driving that tank to empty. When it comes to exhaust emission limits, there's not much further that could be done to significantly reduce those exhaust emission limits. But for refueling control, what we see is that there are simple technology solutions that could control 98% of those refueling emissions with the simple adoption of the onboard refueling vapor recovery systems. And so refueling emissions are an important source, but they can be effectively controlled with the right regulatory process. Finally, diurnal emissions are significant in India. So I spent quite a bit of time talking about refueling emissions, but I also want to talk about the importance of the emissions that occur when the vehicle is simply parked. And this is because it is the combination of high temperatures and high vapor pressure fuel that creates unique challenges for India that do not occur in any other regions of the world. European standards and test conditions are not sufficient to resolve these challenges. If there's one point that you could take away from the webinar today, it's this one, is that the European standards and test conditions are not sufficient to resolve the challenges that occur in India. More canister capacity is needed to absorb the petrol vapors and to contain them and prevent excess emissions in use. When it comes to temperatures, India is not comparable to Europe. And so a different approach is needed for regulating evaporative emissions. Because as we started the webinar, temperature is an incredibly important parameter when thinking about the potential for evaporative emissions from a volatile source such as petrol. The current certification profile for the hot soak and diurnal test in Euro 6D and Euro 7 is a 20 degrees Celsius to a 35 degrees Celsius temperature profile, which is shown down here in the bottom right in black. This certification profile is representative for a lot of European cities. So what we did is we looked at temperature data going back several years across a variety of European cities. And what you'll find is that this chart shows the fraction of days within each year where the temperatures are greater than that 35 degree limit of the test. And so for most cities of Europe, you'll find a very small fraction of days exceed that 35 degree Celsius threshold. Madrid being the one that has the highest frequency, approaching about 8%. But if we look at India, we see a much more different picture, where Indian summers can be quite hot, ranging between 40 degrees Celsius to 45 degrees Celsius. And you'll see that across a variety of Indian cities, a significant fraction of the days, in some cases more than 35-40% of the days of a year, are exceeding that 35 degree Celsius threshold. And that is incredibly important when thinking about evaporative emissions, because the evaporative emissions increase exponentially with temperature. And so it's important that the certification tests are conducted during conditions that are representative of the conditions where the vehicles would be parked. These higher temperatures result in higher fuel temperatures, which increases the evaporative emissions. And so therefore, the in-use evaporative emissions have the potential to be much higher than the certification tests in India. And if you just look here again at the current certification profile versus a profile that's representative of one of the hot summer days in either Delhi or Kolkata, you again see that the certification temperature profile is much lower than what is actually observed in a lot of these regions. So one recommendation that could be considered within BS7 is to consider a different temperature profile, shifting the certification temperature profile upwards to account for the warmer climate of India within the certification test. And the reason this is important is because the diurnal vapor generation, again, this is the vapor that comes from a vehicle that is parked, can be more than 150% higher in India conditions relative to Europe. The amount of vapor that's generated from a fuel tank can be accurately modeled. And this is, again, based off a long history of laboratory experiments where fuel tanks have been heated to certain temperatures with different fuels. And through a variety of experiments, you can build predictive models to estimate the vapor generation that would occur from a fuel tank under a given set of conditions. And one of the common models that's used in the industry is called the Wade-Reddy equation. And that is what I've used here to estimate the fuel vapor that's generated under a given set of conditions. So in all of these examples, it's a 60-liter fuel tank, so a fuel tank for a light-duty vehicle, that's filled 40% with fuel. And that 40% number just comes from, that's the average generally the average volume of a fuel tank. Not a lot of people wait until their fuel tank is completely empty before they refill it. So 40% is meant to be a representative average estimate of fuel tank volume. And then you can look at different fuels. So the first two that are shown in black are conditions that are representative of Europe. So it's a 60 or a 65 kPa fuel that could range between E0 to E10. And it's at 20 to 35 degree Celsius diurnal temperature profile. Under those European conditions, a fuel tank would be estimated to generate between 25 to 30 grams per day of fuel vapor. And so when canister systems are being designed for vehicles under these conditions in Europe, they're ensuring that those canister systems can capture between 25 to 30 grams per day. And if it's a 2-day test, you would multiply those numbers by 2, making sure that the system could capture between 50 to 60 grams per day. If we look at India, which again has higher vapor pressure fuels of E20, so that's between 65, it could be as high as 70 kPa E20 fuel. And India has warmer temperature, so depending on the region, that diurnal temperature profile could be 25 to 40 degrees, or it could be 30 to 45 degrees in regions such as Delhi. And under those conditions, you'll see that the vapor generation per day is significantly higher. So in the case of 43 to 64 grams per day. And so one of the challenges here is that if a canister system is being designed to only capture 25 to 30 grams per day, but in reality, we're seeing 43 to 64, you can see a case here where these canister systems could quickly become saturated and be sources of evaporative emissions. And so an evaporative emissions canister that's designed to European type conditions and limits would be undersized for India conditions, which has the potential to result in higher canister emissions in use. And so to demonstrate this, we've performed laboratory testing to show that systems designed to European standards would have higher emissions in those India conditions. And so, as we mentioned earlier, evaporative emissions can be tested in sheds. They can be tested, you could test the full vehicle in a full vehicle shed, but you can also test just the fuel system. So that'd be the fuel tank, the lines, and the canister system, in what's also referred to as a mini shed. These mini sheds are used in canister development, for during the design process. And so in this case, we're using a mini shed, and you can see in the figure on the upper right, there's a 60-liter fuel tank, or 50-liter fuel tank, sorry. This is filled with E20 fuel and a Euro 6D canister. So a canister that is designed according to the Euro 6D procedures, which is about 1.2 liters in size, is added to the fuel tank vent. These canisters are preconditioned prior to the test to represent the same type of preconditioning that occurs during the full vehicle test. So the canisters start at the same condition prior to each test, and so that there's consistency. The system is essentially equivalent between the tests. The only variable that's different is, in this case, the fuel vapor pressure and the temperature profile. So we conducted 2 tests with this system. The first was a certification test condition. This was an E20 fuel of 60 kPa with a diurnal temperature profile of 20 to 35 degrees Celsius. So this would represent one of the scenarios that could take place during a certification test. We then repeated the test under an India-specific condition. So this is an E20 fuel that has a slightly higher vapor pressure of 65 kPa and a diurnal temperature profile that might be representative of a city like Delhi during the summer of 30 to 45 degrees Celsius. If we look at the chart on the bottom, what we're looking at is the canister evaporative emissions. So that's the evaporative emissions that were measured in the mini shed over the course of this test. And we conducted 2 days of diurnal testing. So it was a cycling of the temperature profile over 2 days or 48 hours. And we measured the emissions from the mini shed at day 1 as well as at day 2. And so if we first look at the certification condition, which is shown in blue, what you'll find is that the day 1 plus the day 2 emissions are less than the 2 gram limit. So the certification, remember the current Euro 6D certification is that the day 1 plus the day 2 emissions have to be less than 2 grams. And so what we find is that this canister, the Euro 6D canister, is designed to pass the certification test. The emissions from day 1 and day 2 remain well below that limit. But if we take that same canister and fuel system and we test it under the India test condition, we find day 1 emissions that are approaching 4 grams, which are 14 times higher than under the certification condition. And then for day 2, we find emissions even higher of 22 grams, which are 40 times higher than the certification condition. So what this test is showing is that these higher temperatures and higher vapor pressure fuels are generating a lot more vapor in that fuel tank, and the canister is not designed to capture all of that fuel vapor. And so starting even at day 1, that canister is becoming saturated, and you're having 4 grams of emissions escape. By day 2, the saturation is even higher, to where now we have more than 22 grams of vapors escaping. So the combined day 1 plus day 2 emissions is more than 25 grams of fuel vapor are being emitted from this Euro 60 canister over 2 days of parking. And so if you again put that in terms of volume, it's around 36 milliliters of fuel that's evaporated, or approximately 4 rupees over just that 2-day parking event. Again, we can compare this to the exhaust hydrocarbon emissions that would be emitted from a vehicle that drives an average of 33 kilometers a day. So this is just taking the average driving distance for a vehicle in a day of 33 kilometers and multiplying it by that 68 milligrams per kilometer maximum exhaust emission value. And you come up with, on average, vehicles from the exhaust side would be emitting around 2 grams per vehicle per day. But the evaporative emissions could be as much as 25 grams per vehicle per day. So the potential for the evaporative emissions is more than 10 times the exhaust emissions under these Indian scenarios. And so the diurnal emissions are incredibly important for India. So this is a challenge, but it is a challenge that can be solved. And so what we did is we retested these systems using larger capacity canisters that are designed to control for refueling. This is the onboard refueling vapor recovery systems. And we wanted to understand how these systems could control the diurnal emissions. And so we tested the same laboratory tank, 50-liter tank, E20 fuel. In this case, we used a slightly higher vapor pressure, and we used the 25 to 40 degree diurnal temperature profile. So this specific test was meant to be a more representative condition that could be occurring across India during the summer period. We did a 2-day diurnal test with the Euro 6D canister, which was the 1.2 liter. And then we repeated that 2-day diurnal test with the ORVR size canister, which was 2.1 liters. And again, if we look at the Euro 6D canister, and again, these test conditions are off cycle, or meaning they're not the certification test condition, because it's slightly higher RVP and a slightly higher temperature profile, shifting at 5 degrees. You'll see that the Euro 60 canister on day 1 had emissions that were less than 1 grams, but by day 2, that canister becomes saturated and is emitting around 4.4 grams. So under these conditions, the Euro 60 canister emitted around 4.4 grams over day 1 and day 2, exceeding the 2 gram per test limit by more than 2 times. And so again, it's just another data point confirming that Euro 60 canisters are undersized for the India conditions, and they can quickly become saturated even at just slightly higher temperatures and higher vapor pressure fuel. But for the ORVR canister, you can see that day 1 emissions were not detectable, and day 2 emissions were around 0.1 grams or 100 milligrams. And this represents a 97.5% reduction, or around a 98% reduction in the diurnal emissions under these conditions for the India scenario. So what this shows is that the larger canister capacity matters when it comes to diurnal emissions. you could achieve more than 98% reduction of those emissions, which are representative of the Indian scenario. And in addition to that, you also get the 98% control of those refueling emissions that we saw earlier. And so really it comes down to the size and the design of the canister is incredibly important for controlling the evaporative emissions from vehicles. And the size and the design of the canister is dependent upon the regulatory test procedure and the limits. And so as we go back to that slide where we showed the difference in regulations across the different regions, when India is thinking about Bharat 7, the evaporative emission test procedures and limits need revision to enable the adoption of larger canister systems to improve the control of these evaporative emissions. And there are multiple options that could be considered. The first of which is adopting the refueling standard. The test procedures for the refueling standard already exist in the US, Brazil, and China. These test procedures are virtually identical across these regions. The only difference is China uses the WLTP drive cycle. And so the test procedures exist. It's just a matter of adopting them in the regulation. And this is the ideal solution because it ensures 98% reduction in refueling emissions, but also providing a significant reduction in the diurnal emissions at temperatures and conditions representative for India. Another option that could be considered is simply revising the temperature profile of the diurnal test to be more representative of the Indian conditions. So rather than testing over 20 to 35 degrees Celsius, for example, which is the Euro 6D profile, it could be shifted higher to be more reflective of India, such as shifting it just by 5 degrees to 25 to 40 degrees Celsius would be a significant change that would drive additional control technology on the vehicles. And this would ensure that canisters are being designed and sized for the diurnal conditions that are occurring in India. And then finally, another option that could be considered is lowering the limit of the diurnal test. US, Brazil, and China already have vehicle solutions that certify to levels less than 0.5 grams per day or lower. Again, showing that the technology is achievable and able to be incorporated onto a wide variety of vehicles, including vehicles that adopt high ethanol fuels, as is the case for Brazil. And so some of the concluding slides here are just that evaporative refueling emissions are effectively controlled across the world. One of the most effective ways to control evaporative and refueling emissions is with onboard refueling vapor recovery systems. You could also use larger canister systems as another option. And there's been more than 25 years of successful implementation of these solutions in global markets. They're cost effective and have been demonstrated to reduce emissions by more than 98%, while also controlling these hot soak and diurnal emissions to levels of less than 0.3 grams per day. So if we think about the current situation in India, the Bharat 6 vehicles contain a one-function canister. That could be further improved by the adoption of ORVR, which is a two-function canister that captures the emissions from refueling, in addition to those excess emissions that occur from diurnal emissions during warm temperatures. These petrol vapors are stored in that canister until the vehicle operates, and then they're used by the engine for combustion. So more than 98% of the refueling vapors can be captured, requires no maintenance, and the cost of the control technology is recovered by the consumer in fuel savings. So as we noted earlier, between every refueling event is between 5 to 10 rupees. And then every 2-day parking event during the summer could be as much as 4 rupees. And so over time, over the life of a vehicle, those small amounts add up and can quickly cover the cost of the system, which is a larger canister system, such as the one shown in this picture here, adopted on a vehicle. Because all vehicles already have a canister system, it's simply changing a few design elements, making the canister slightly larger, changing a few of the lines. The cost of shifting the technology to like an onboard refueling vapor recovery system is generally less than 30 euros or less than 3,000 rupees. So that cost can be recovered just from the fuel savings alone. So in wrapping up, the key messages that from the webinar today, Our evaporative emissions are volatile organic compounds that evaporate into the atmosphere. They occur during parking, during operation, or the refueling of any vehicle that contains a petrol fuel tank. So this includes two-wheelers, three-wheelers, commercial vehicles, passenger vehicles. Any vehicle that has a petrol fuel tank will have evaporative emissions. For India, it is the combination of high temperatures and high fuel vapor pressure that creates unique challenges. The European standards and test conditions are not sufficient to resolve these challenges. Diurnal evaporative emissions from canisters that are designed to Euro 6D could increase by more than 40 times when tested under conditions that are common to India. And this can be more than 20 grams per vehicle per day, which is more than 10 times the amount that comes from the tailpipe. We expect Euro 7 canisters will be similar to Euro 6D, so simply adopting Euro 7 would not be the solution to the challenges that India is facing. Without sufficient control, petrol and money is simply being wasted. Exposure to evaporated petrol is harmful, and it reacts in the atmosphere to form ozone and particulate matter, creating haze and smog. And so this is, again, an important category of emissions with important impacts that can be effectively controlled. So simple changes to the Bharat regulations can lead to the adoption of improved control technology. Larger canister systems are needed to not only control the refueling emissions, but also prevent excess diurnal evaporative emissions during conditions that are common in India. And so finally, systems such as ORVR could capture refueling emissions by 98% and control the diurnal evaporative emissions by 98%. These systems cost less than 3,000 rupees, as evidenced from impact assessments done by the US EPA as well as the European Commission, and they require no maintenance for the life of the vehicle. So with that, I really appreciate your time today and would be happy to now take the floor for any questions you may have. Thank you.
Thank you, Terry, for that very comprehensive and informative presentation. I have to admit, some of the slides were no less than eye-openers for me. And especially, and thanks for putting things in perspective. Sitting in the US, putting things in perspective in Indian value terms for the audience here. So, I can imagine if you're refueling a 50-liter gasoline tank could lead to a loss of 7.5 or 10 rupees per refill if there is no efficient capturing of the evaporative emissions, right? So that's
Yes.
I mean, and as much as, okay, in absolute terms, for one filling, it may not be a significant value, but if you multiply that with the number of vehicles filled at that particular petrol station, a gas pump, for example, it could be a significant thing, which is, which can be avoided by efficient use of the options that you mentioned. So thanks a lot, and thanks for also sharing the suggestions that you made for the in authorities in Indian regulatory framing bodies to consider the kind of the values which would be more suited for Indian conditions than rather just pick up from where the European norms are because of the different climatic conditions that you mentioned. So indeed a very, very comprehensive presentation, Terry, and congratulations on that. So let's also dip into the Q&A box and see. Okay, good to see. As expected, a good number of questions. Okay, first off, one question from India's largest passenger vehicle maker, someone from the company, Maruti Suzuki. The question is, by the way, the gentleman is Vivek Kumar, and he asks, what strategy for EVAP and purging in an HEV, in an XHEV is trending globally, especially when we use turbo engine in HEV, hybrid electric vehicle, he means.
Yeah. So the question is around hybridization and hybrid electric
Right.
vehicles.
Right.
Correct. Yeah. So and the as I think everyone knows, that hybridization is increasing across the world due to the fuel economy regulations, which drive just ever increasing fuel economy of vehicles. And so what we find is that even for hybrid vehicles, so vehicles that have the battery plus the fuel tank, that most hybrid vehicles in our experience are still include petrol engines. And so evaporative emissions are still an important aspect to control for even hybrid vehicles. And one of the challenges that is recognized when it comes to hybrid vehicles, where a period of the engine is going to be operated by the battery versus the engine. So the opportunities for purging, remember I said purging is a very important aspect of the evaporative emission control system, is purge. And so as vehicles become increasingly hybridized, the available purge volume or time for purge does become less. And so automakers have to do some more advanced calibrations around purge to account for that. But what we've seen, particularly in the U.S. markets and other markets, are that even with increasing hybridization, the evaporative emission limits are able to be maintained with the control technologies. And as a company of our own, we're continuing to develop innovative products to handle. To basically increase the capacity of carbon and the ability of that material to purge, to adopt to the changing needs of the regulatory environments. And so again, recognizing hybridization is becoming a very important part. We are developing solutions, activated carbon solutions, that can enable the standards to be met even under those conditions of low purge. So that's just some of the developments that we see from just a carbon technology perspective. It's advancing. And then as more hybrids enter the market, the experience around calibrations of purge is also advancing.
Our next question is from Rajiv Kaushik. He asks, the E20 fuel RVP is 70 kPa, but during homologation testing, considered reference fuel E20 with 60 to 65 kPa. That means in actual vehicle emissions are more than how to control the protect the environment.
Yeah, so it is one of the challenges that is observed, right? So if certification testing is done under, for example, conditions of 60 to 65 kPa, so canister systems are designed for a 65 kPa fuel, then if in use, the fuel used is 70 kPa, there is the potential, yes, for higher evaporative emissions than the system may have been designed for. One of the ways that manufacturers or canister suppliers could accommodate that is when they're designing systems, they include a safety margin or some type of margin in the design of those systems to account for that. But that may not always be a guarantee. And so that's why it is oftentimes very important that the certification test conditions be as representative as possible for what is expected to be in use. And that's, I think, the RVP difference is one area that we've noted as a difference, but then also the temperature profile being another. So it's just some important considerations that could be thought about in terms of just even the certification RVP is something else that could also be thought about in terms of the regulation. And that could be changed, for example, to 70 kPa to solve that gap.
Sanjeev Bhushan asks, is there any changes in the diurnal temperature profile planned for Euro 7? And is there a limitation on the number of days for the SHED?
So for the Euro 7, no. And one of the reasons for that was just if you think about Europe as a whole, and the graph that we showed, and I could probably even go back to it if it's possible, of just the temperature profiles. I think one of the challenges with Europe is shifting the temperature profile in Europe. There may be claims that a higher temperature profile may not be representative for a lot of the European cities, because again, many of the days across a lot of European, particularly the northern European climates, will not have days that exceed that 35-degree temperature profile. And so with Euro 7, it was not a discussion about changing the temperature profile. During the development of Euro 7, one of the things the Commission initially proposed was the refueling standard. So the onboard refueling vapor recovery, that was initially proposed by the commission because they recognized it would control the 98% of refueling emissions, but then they also recognized the fact that if they adopted the ORVR system, they didn't have to change the temperature profile. That extra canister capacity would help solve the diurnal evaporative emissions that occurred in even some of those warmer climates. So countries like Italy and Spain and France that have higher temperatures, having those ORVO systems would have provided that excess capacity that they would need to mitigate that. So that was why the commission initially proposed the options that they did. It wasn't a discussion there about the temperature profile. The question about the limitations of the sheds have the ability to run to higher temperatures, up to I think 50 degrees Celsius, and then they can run for any number of days. There's no limit to the number of days that a shed could do a diurnal. It's just a matter of the test burden. So I think these are full day tests, 24-hour test. If it's a 1 day, it's a 2 day, 48-hour test. If it's a 2 day test, and so it's just a matter of how many sheds are available and the timing to do the testing is why oftentimes you see the limit, at a maximum of either 2 days or in the case of the U.S., 3-day testing. I think regions have explored looking at even more diurnals than 3 days, but it just becomes an added burden for doing that type of testing because again you're taking up a shed asset for almost an entire week if you're doing more than 2 or 3 days of testing. So those are just some of the compromises that have to take place during the development of standards. One objective is always to try to minimize test burdens where possible, but try to make the regulations also as representative as possible. So those are the balances that regulators have to take.
So another question is there I'm not sure whether you would be able to answer this because this is specific to India, but anyway, in case you're following it very closely, is there any upcoming regulation planned for two-wheelers also for India?
To my knowledge, I've not come across anything on two-wheelers. The most recent example that I'm aware of globally was the reference I gave for California. That was looking at, I think India most recently adopted the Euro 5 standards for motorcycles, which are, if you look across the world, the most stringent regulations for two-wheelers. When it comes to evaporative emissions, the region that was looking at these closely was California, going back into the 2022, 2023 timeframe. They were looking at requiring the Euro 5 procedures to be adopted and then taking it a step further, looking at further improving the evaporative emissions by requiring essentially instead of a 1-hour test to require multiple days of diurnal testing. So that was the initial proposal that was put forth from California back in 2022, but has since paused again due to some just the politics that are taking place in the U.S. There's currently a pause on a lot of the regulations coming out of California. So for the moment, that proposal stays on pause. I'm not aware of other discussions, but the way BS7 is currently structured is that it includes light duty vehicles as well as 2- and 3-wheelers and quadricycles. So it's not uncommon that they would consider looking at 2- and 3-wheelers in the review of the upcoming BS7. I'm not sure if they've announced intentions for doing that, but given that BS6 includes all categories of vehicles, it's a possibility that it could be discussed within BS7.
Okay, one simple question. For the measurement of evaporative emission, what is PF?
That is the permeability factor. So the way that the European regulations are written is that you either use a default value. That default value is 120 milligrams per day, or the manufacturer has the ability to conduct a specific permeability test, which is a test procedure where they can determine what that permeability factor is for their systems. So it's a factor that is designed to account for the permeation that we noted earlier, and that's particularly important when you start adding ethanol fuels. So when Europe moved to E10, this permeability factor was something that got incorporated into the Euro 60 test procedures.
All right. Another question is from Rajan Riker. Any thumb rule in the selection of the canister size And is selection of the canister size based on the fuel tank capacity?
That's one rule of thumb, but it can be more complex than that. But one of the key driving factors, yes, is the fuel tank size. So you'll see that canisters often scale with fuel tank size. I think I noted that in this slide here is just one example of that. But the regulatory standards are the other driver. So when you're designing a canister system, you need to understand what are the maximum amount of fuel vapors, a scenario that represents what is the maximum amount of fuel vapors that could be generated. So if there is no refueling standard, the canister is sized based off the diurnal vapor generation, and essentially what the certification temperature profile is, what the fuel vapor pressure is. Based on, again, the Wade-Reddy equation, you could determine essentially how much vapor is being generated from the tank during a given set of conditions. And then from that, you would determine what type of size canister system is going to be needed to capture that fuel vapor. So that's one aspect. But then if you have refueling control on the vehicle, that's another aspect in designing a canister, because you think the refueling event only takes place within a couple of minutes. So a large volume of vapor is needing to come through a canister in a short amount of time. And so the canister system is designed primarily for that refueling event, to capture that amount of vapors within that short amount of time. And then they're also looking at then, is that canister size sufficient then to also capture those diurnal emissions? So fuel tank size is one factor, but then what particular source that has to be controlled is the other factor. So if it's refueling or if it's diurnal, those are both in consideration in designing a canister size.
Here's a question which could very well a question from me as well, because I would have asked the same. This is from Prashant Pawar. Could you elaborate more on ORVR, how it works? Is there a pump inside? Does it require modifications to fuel filling nozzle? And also, can it be retrofitted into an existing car?
So I do have a slide. Let me find it here that can go into a little bit more detail.
Yeah, please. And if you can share your screen.
So in terms of modifications, so one of the primary modifications relates to the canister size, as we noted earlier. So ORVR systems typically require a larger canister system to account for the fact that you are pushing a lot of vapors into the canister within a short period of time. The other components that are typically required are a larger diameter tube going from the tank to the canister. Again, because you need a route for this vapor generation. You don't want the vapors to be coming out the fill pipe. You want them to be directed to the canister. So what typically happens is this diameter is reduced and this diameter is increased. So essentially it allows the vapors to pass through the valve here into the canister versus come here. So this is primarily filled with liquid fuel as it's coming in, so the vapors don't escape here. They will go through the canister system. So you can see here there's fill pipes. In some cases that can be savings if you're decreasing the size. If you're increasing it, it can be a cost. So there's components like an anti-spitback valve, overflow protection valves, and the carbon canister. So these are all elements that need to be added when it comes to an ORVR system. And again, this is coming from the European Commission's kind of cost impact analysis when they were looking at proposing ORVR to come up with the range between 16 to 30 euros for those component changes. And so again, because you're putting a larger canister on the vehicle and it does require other material modifications, it's not something that can be easily retrofitted to a vehicle. And one of the key reasons for that is if you have a larger canister system, it's going to need purge. You want to make sure that system can be adequately cleaned, between refueling events or purged. And so it would require essentially additional recalibrations on the vehicle as well for the purge for that larger canister system. So it's for those reasons that as much as we would like it to be just an easy retrofit solution, it's oftentimes not, just because of the fact that there are calibrations that involve purge that have to be addressed, as well as ensuring, again, that the vapors are indeed routed to the canister versus coming out the fill neck. So I hope that answers the question.
Thanks for the explanation, Terry. Prakash Sardesai asks if Europe is not agreeing to ORVR, uh, how can we expect Indian legislators to agree for the same? That's his comment.
Yeah, it's a challenge considering India has historically followed Europe. I
European
think
norms.
European norms. That's been the historical case. And in this situation, what it would require is the adoption of an additional test procedure that does not exist in the European norms. And so it would just require the decision to make a change that is different from the European norms. The rest of the European norms could still be followed. It's just adding a supplemental procedure to those European norms. And again, when it comes to ORVR, it's not like India has to create its own test procedure. The test procedures that exist are consistent across all the regions that have adopted it. And I think some recent examples of just that decision to deviate from European norms has been taken by other nations. So Brazil being one, China being another. They historically had followed European norms, but due to unique challenges within their countries, China was a strong desire to improve air quality and create, the blue sky days, as they referred to, going back many years ago. They made the conscious decision to deviate from the European norms because they recognized that the European norms weren't providing the benefits that they needed for their country. And so I think the same thought could occur within India. It's just it's a change. It's just a challenge and barrier that exists, that a decision has to be made to essentially deviate from a longstanding tradition of following European norms. But when it comes to ORVR, it could be just a simple supplemental test procedure that is added to the existing regulation. Because and when the European Commission was looking at proposing it, they were looking to the regulations that were already written in the other regions of the world to simply adopt them in. So from that perspective, yes, it is a challenge, but is one that could be overcome if the need is justified.
Another question from Prakash is that is it that day 2 increases diurnal emissions much higher exponentially than day 1?
Typically, day 2 emissions are indeed higher than day 1, and that it comes down to simply that canisters are designed to capture a certain amount of hydrocarbon vapors, and so it's essentially not a step change type process. So as a canister gets filled with fuel vapors, it starts having an emission profile. So it doesn't take until it's completely saturated before it emits. And so as it fills up, it will start emitting a small amount of emissions. But then as it reaches saturation, essentially is what we refer to as called breakthrough, then you have significantly higher emissions. So oftentimes why you see such a big step change in the data I was showing was because you're essentially reaching that breakthrough point of the canister, by day 2. So the canister may have been designed to capture 1 day of those emissions, but if you add another day to it, you've hit the breakthrough. So then that's when you start seeing that exponential increase. And so what you're trying to avoid is you want to design a system that is not reaching breakthrough over a period of at least 2 days of diurnal, because that typically captures most of the parking events. I've not seen recent activity data out of India to get an estimate of exactly how many days vehicles typically park. But in other regions of the world, what I've seen is that 1 to 2 days of parking captures a majority of the parking events, and so you want to make sure that system is essentially not reaching breakthrough after 2 days.
Somnath Nagore asks, do you have any study or comparison between 2 hours versus 24 hours shed test for two-wheelers? Any insights there, or you have, or
between the 2 hours and
20,
what was the
24 hours?
The only data I have, and again, I do have a slide here. I think let me just pull it up. Am I still sharing? So I can share one of the slides that California had presented back when they were doing their proposal. This is the only data that I'm aware of
Mm.
regarding two-wheelers. So this was a test on 10 different two-wheelers over a 3-day period, and what they were looking at was does a single day of testing reflect emissions that could occur over multiple days of parking? Because one of the concerns, particularly out of California, was that people typically only drive their two-wheelers on weekends. I know that's different from the Indian condition where they're often driven every day. And so, but what this does show is, again, day 1, day 2, and day 3 type of emissions from a variety of different two-wheelers, which were designed for the current, I think, 1-hour test. And so they were showing that, again, as you might expect, the more days the vehicle is parked, the higher the potential for the evaporative emissions. And again, this was over California has a higher temperature profile, similar to what we were suggesting India look at. California tests up to 40 degrees Celsius because California has higher temperatures than other parts of the U.S. So California actually has their own temperature profile that represents a summer profile, as well as they have their own fuels. And so this is the data that I'm aware of. We haven't done any testing of our own in recent years looking at two-wheelers, but there would be a difference between the current kind of 1-hour test versus multiple days of diurnal testing.
Okay. Another question from Prakash is that if limit is increased to 3 grams per test with 2-day cycle from 30 to 45 degree diurnal, will that give a reprieve to industry for revised larger canister design?
I would not suggest increasing the limit. I would not recommend increasing a limit. The intent of increasing the temperature profile or decreasing limits is to encourage the canister systems to be sufficient to capture those vapors. If you increase the temperature profile, but then in parallel increase the limit, they're essentially offsetting each other. And so what you need is essentially more stringent regulations to drive increased technology adoption. And from what we've seen, particularly in other regions of the world, California being one of those regions, where even at higher temperature profiles, the emission limits that are much lower than 2 grams per test are achievable. So we see that in the U.S. as well as Brazil and China, that emission levels of 0.5 gram per day or less are possible. And so our recommendation would be that the temperature profile would be shifted upward, but the limit value does not change.
All right. Okay. Next is Naran Prakash Ganpati asks, why should RVP increase with ethanol addition in petrol, though the RVP of E100 or flex fuel is lower?
Yeah, so it's a complex phenomenon that deals with the commingling of the two different fuels that leads to the increasing vapor pressure generation. So it's a commingling effect, essentially, that the addition of ethanol, which is a polar molecule, to the petrol increases the tendency just for, again, the molecules to have higher energy and to evaporate. And that occurs at smaller amounts of ethanol. So as you put more and more ethanol into the fuel, that effect diminishes over time. And that was what was shown with the graph here. I could pull it back up of the vapor pressure curve. So you see that very small amounts of ethanol have the greatest impact, but it takes actually quite a significant amount of ethanol before that impact diminishes. And it's essentially it's molecular interactions is the simplest way I can describe it. They call it a commingling effect that leads to that vapor pressure increase. The only way that you can manage that, if you did not want the vapor pressure of the gasoline ethanol blend to increase, you have to do what's called RVP control of the base petrol. And that is something that the US and California in particular requires. It's what's called reformulated gasoline. They require specific limits on the base petroleum so that when ethanol is added to it, it does not lead to an increase in the RVP. So that is one of the strategies that areas like the US and California use, is they manage the RVP increase. They say that, adding ethanol, you cannot have an increase in the vapor pressure. So you basically have to pull out some components in the base gasoline. So like butanes or pentanes, you have to pull some of those out to bring the vapor pressure of the gasoline down, something in maybe like the 50, 55 kPa range, so that when you add ethanol, it stays at around 60. So that's one way that you manage it. The other way is you just recognize that it is an important effect, and you design your systems to account for that increase. So there's different strategies for how you can deal with the effect. The simplest one is on the control side, because it is very difficult and costly to control the vapor pressure of the petroleum. So that is a very costly type of control strategy to do RVP control of fuel.
Okay, another question. What is NHMC emissions and how is it measured?
So NMHC refers to non-methane hydrocarbon. So when they're doing exhaust emissions, it's essentially measuring the non-methane hydrocarbon component. And that's the same as what would occur for evaporative emissions. So you'll oftentimes hear them referred to as non-methane hydrocarbons or volatile organic compounds. Those are the two common acronyms. And the way that, at least for the evaporative emissions side, they're measured is with an instrument called a flame ionization detector, or an FID. So it is just a piece of specialized equipment that is designed to measure those non-methane hydrocarbon species.
Couple of questions from Pradeep Bagade. What are the procedures of regulation to measure evaporative emission during regular COP testing? And why vapor pressure for E20 petrol is more compared to ethanol 100?
The latter part of that question is just what we described before, is that ethanol itself has a vapor pressure as well as petrol itself. But you mix the two together, you get that commingling effect that leads to an increase in vapor pressure that's higher than either one of the base components. So that's just it's just a known fact that when you mix these two together, particularly in small quantities of ethanol, it leads to an increase in the vapor pressure. Remind me, what was the first part of that question?
Okay, I'll come again. It is what are the procedures of regulation to measure evaporative emission during regular COP testing?
Yeah, so the conformity of production testing, or COP, it follows the same procedures as the certification test. So it would be the type 4 evaporative emissions test, which currently for India is the 1-day test using the reference fuel. So in this case, it's the E20 reference fuel. So the vapor pressure of that fuel could be between 60 to 65 kPa, and it's a 1-day hot soak and diurnal shed test with the limit of less than 2 grams. So the COP procedures mirror the certification procedures.
When evaporative certification procedure for car in Europe has changed from tank heating to day-wise diurnal test, and what is your thought on 2 hours two-wheeler shed test?
You're talking about the shed two-wheeler test, and that's a tank heating test, correct?
Yeah.
Yeah. So my thought there is, I think the more representative test would be a full diurnal test to most accurately simulate what occurs during a typical hot soak and diurnal procedure. So the 2-hour test is essentially an accelerated version of that, and so I think it would, just the more representative test would be doing the full doing that over a full 24 hours. That would be my suggestion. And just looking at, again, the most recent agency to look at this in significant detail was California, and their suggestion was also to shift to a diurnal test.
Vishav Sharma asks, can we install vapor capture at pump, and how?
Yes, so that is what we refer to as the stage 2. So that's this system here, and I do have a slide that goes through essentially what that means in a little bit more detail. So this slide here. So this is what we refer to at the capture at the pump. So A stage 2 system has a different nozzle, and that nozzle is designed to dispense the liquid gasoline, but to also pull an active flow, and that's done by putting essentially a pump in the dispenser that pulls flow through this nozzle. And so as you refuel, the vapors are intended to come out of the tank, again through the gas cap area, but then get pulled by this nozzle in. One of the challenges, though, with these systems is while they can pull the vapors from the vehicle, it's really difficult to perfectly match these conditions to where the amount of air that's being pulled perfectly matches the amount of vapor that's being emitted by this tank. If those two do not perfectly match, you end up in scenarios where either you could have excess air being ingested, or you can essentially have excess vapors being emitted. And this is why, again, it's really challenging for a stage 2 system that's doing this active pumping to reach efficiencies that are at, near 100%. The real world efficiencies of these systems typically range between 50 to 70%, just due to, again, there's a lot of variables that can impact these flow rates. And again, because you are actively pulling vapors and you're pushing them back down into the underground storage tank, there could be situations where, particularly if you're pulling in a lot of excess air, that you put clean air into this underground storage tank. This tank then has to reestablish equilibrium, which means vapors are generated, and that increases the pressure of the underground storage tank. And if there's not a control on the vent stack, they just come back out the vent, as we saw in one of the videos earlier. So stage 2 is a solution to get some control of the refueling event, but it's not recognized, at least within the US and other regions like China, as the most effective measure for getting refueling emissions. Because again, the in-use efficiency of these systems has been documented to be anywhere between 50 to 70%. So there's just a lot of challenges. You do get some control, but you do not get as efficient of control as when you control the vapors on the vehicle through a canister system. Because when you do that, you don't have to worry about all of these different conditions and trying to balance everything perfectly.
Terry, I thought maybe an hour and a half would be more than enough for us to cover all the questions and of course after your presentation. But I have been proven wrong because the engagement level is so high. So we will, with your permission, we will exceed the webinar time by about 5 minutes. Is that okay?
Sure. Yes, that is fine. And then if there are any others, I'm happy to also answer them written as well.
All right, great. So we are left with only 2 more questions. One of them is from Bishop Sharma, who asks, any technical solution to capture vapor at petrol pump? Instead, can it be more cost effective?
No, so the only solution at the petrol pump is the one that I'm showing here, which is stage 2. And if you look at the representative cost effectiveness between what it costs to do all the capital infrastructure changes. So with stage 2, you have to change the gasoline dispenser, you have to change the gasoline nozzle. You also have to excavate and put in new piping to direct the vapors to the underground storage tank. So there's a lot of upfront capital costs that are associated with installing a stage 2 system at the gasoline dispensing facilities. And then these systems also require, to keep the efficiency at the levels of at least 85%. The experience from US was that significant amounts of inspection and maintenance were needed. These systems are not, the nozzles as well as the systems can lose calibration. And so again, it's about perfectly balancing the vapor coming out of the fuel tank with the amount that's pulled. And if that calibration is off, you have the excess air or the excess emissions coming out. So it's the analysis that I've seen looking at the differences in cost effectiveness between stage 2 systems as well as ORVR systems are that the ORVR systems come out ahead on the cost effectiveness. And I'm not sure if I have a slide on the specific values, but this slide here just shows an example of the type of certification and maintenance that's required. and what was required by European standards versus US standards. And what you'll see is that, there's a lot of rigorous inspection that's needed to get to efficiencies of 95%. And those are currently not being done, at least on the European levels. And so from a cost effectiveness point of view, the ORVR systems are more cost effective than stage two over the long term, which is why from the US perspective, the US EPA moved away from stage two. It's been decommissioned across the US in favor of the ORVR technology.
I see. Okay, good to know about that. Thanks for updating us. So last question in this session is, what are the purging strategy for turbocharged HEVs? This is from Vivek Kumar.
I am not aware of the specific turbo. That's a question I can get back to them on, because I'm not aware of the specific purging strategy for wind turbochargers.
So, I mean, really, Dr. Terry Latham, thank you very much indeed for taking us through not only your very comprehensive presentation, but also educating us on so many other factors, aspects of this very interesting topic of the webinar today, which is need and solutions for controlling evaporative emissions in the Indian scenario. And also very timely, considering that we are also preparing here in India for the next level of emission regime, which is BS7, and there are some new kind of regulations related to emissions, including from let's say tires, for example, tire particles and tire dust, brake dust. So yes. It was a very informative session that we had, and as I mentioned earlier, 1.5 hours I thought will be a little too long, but the session proved to be otherwise. But really appreciate you taking time out, and especially in your time zone, really starting the day very early for us. Much appreciated, Terry, and wishing you and your teammates all the very best from all of us here at ET Auto. And look forward to meeting you in person sometime. And a big thanks to all our attendees here. At one point, there were over 100 of them. Really great to see this very strong response to this first webinar of this new series, co-organized by ET Auto and ECMA. Thank you once again, Terry. Any last message from you?
Yes, just again, thank you for the opportunity and the platform to speak about this important issue. And I just want to thank everyone, for the active participation and the questions. Really appreciate the good turnout, as you mentioned. And I said, if there's any other further questions, happy to keep discussing this important topic. But thank you for the time today.
Thank you. And thanks for your time, and have a nice day ahead.